My name is Spencer Waghorn. I'm in Team LASH, LASH, and I'm an aerospace engineering major.
Hi, my name is Andres Groff. I'm with Team Lash, and I'm an aerospace engineer.
My name is Henry King, and I'm an aerospace engineering major.
Hi, I'm Laurel Clements, and I'm an aerospace engineering major.
The goal of this project is to build and test different systems for measuring the distance, temperature, and depth using sensors in the Arduino platform. For each experiment, we had to program the Arduino and construct the necessary system. Our strategy to complete this project was to begin by completing the practice lessons to gain a basic understanding of the Arduino sensors and the platform. We then planned to meet as a group in order to figure out the code and the setup for the experiments. For the water depth experiment, we carried the 5 volts to the breadboard so that we could distribute it to both the water level detector and the servo motor. We did the same with the ground. We then plugged the servo motor into pin 9 of the Arduino and the water level detector's signal output to the A0 pin. This is the code that we used for the combination of the water depth sensor and the servo motor. We basically took the code that was provided in the lesson with the water depth sensor and modified it a little bit so that when it returned its voltage, we would take the percentage of that voltage out of its maximum output, and then we would send that percentage to the servo motor so it would then go to that percentage of 180 degrees so that it would operate as a dial. Here's a video of the water depth sensor working with the servo motor. You can see as we submerge it further into the water, the servo motor moves to the left, and then when we pull it out, there's a small delay, and then the servo motor moves back towards its original position. This is the setup that we used for the combination of the distance sensor and the servo motor. We carried the 5 volts from the Arduino board to the breadboard so that we could distribute it to both the motor and the sensor. The motor was connected to pin 9 again, just like the previous experiment, and Echo and Trig from the distance sensor were plugged into pins 11 and 12 on the Arduino board. We also carried the ground from the board to the breadboard so that we could again ground both the motor and the sensor. This is the code that we used to combine the ultrasonic sensor and the servo motor. We included both the new ping library and the servo library so that we could access the commands for both the sensor and the motor. We also defined the pin locations so that the Arduino would know where to look for the signal outputs. We also used the loop provided in the ultrasonic sensor lesson in order to create pings and read the distance. But each ping was then taken as a percent out of the maximum distance, and the servo motor was then told to go to that percent of 180 degrees so that the servo motor would act as a dial during the experiment. This is a video of the experiment working.
To start constructing our temperature measurement system, we gathered our UNO R3 board, 4-pin LCD 1602 I2C module, 10K ohm resistor, thermistor, potentiometer, 830 tie points breadboard, 4 male-to-male jumper wires, and 4 female-to-male DuPont wires. To build our system, we started by connecting our SCL pin on the LCD screen to the A5 on the UNO board. Then the SDA pin to the A4, the VCC pin is then attached to a positive port on the breadboard, and lastly, the ground pin on the LCD screen is attached to the negative ground port on the breadboard. We then place the thermistor and resistor on the breadboard so that 2 of their ports are in line. To connect the breadboard and the UNO board, we pin the ground on the UNO board to a negative port on the breadboard, and then an A0 to a port that is in line with the resistor and the thermistor. Lastly, we placed 1 male-to-male wire to connect the thermistor to the positive port, and another to connect the resistor to the negative ports. For calibrating our system to display accurate data, we had to alter our code. We took the difference between what the initial output the sensor was giving us and what our thermostat was displaying, and we added that difference to our display temp function, and this made the LCD screen show almost exactly what the temperature of its surroundings was.
There were calibration steps required for each of the 3 experiments that we performed. For the temperature experiment, we had to add 18 degrees to the measured value so that it would report approximately the room temperature. For the water depth measurement, we had to take the voltage that was reported out of the maximum that it could report, and give this percentage to the servo motor so that it could go to that percentage of 180 degrees so that it could act as a dial. We had to do the same thing for the distance measurement, where we took the maximum distance that it could report and then the percentage of that distance that it was reporting and gave that value to the servo motor so that it could go to that percentage of 180 degrees and act as a dial.
A principle I can take away from this experiment is how to build a system using multiple lessons from the Arduino kit. As an aerospace engineer, you will need to use a temperature sensor in the design of an aircraft. The temperature sensors are placed in numerous areas to make sure components of the aircraft aren't overheating and are essential for safety.
For this experiment, we had to use both the servo motor and the water depth sensor. This means that we had to have them both wired at the same time, and we had to make significant changes to the codes that were provided. Being able to write basic code and read and understand code that others have written can be an extremely helpful tool as an engineer. This experiment also gave good practice with coding, and the calculations gave practice with constructing confidence intervals and other summary statistics that can be very helpful as an engineer.